Okay, in this video I want to give a little introduction here to something called a determinant of a matrix. So I've titled this Determinants. Okay, the determinant of a matrix is a number associated and computed from the matrix. Okay, so it's a number that we associate with a matrix. These are only defined for square matrices, however. Okay, so if A is a square matrix, then the determinant of A is sometimes written this way, DET of A, okay? Sometimes people will include the parentheses, sometimes they won't. I will usually include the parentheses there after the DET, so that just stands for the determinant of A. Again, I emphasize here they're only defined for what? Square matrices, okay? All right, let's talk about the computation, okay? One by one matrices, okay? So this is basically a single entry with square brackets around it, right? A matrix being an array of numbers. What is the determinant of the matrix for a one by one matrix? It turns out to be just whatever the entry is, okay? So this is highly trivial here. So in this example here, if I've got the matrix A being just the element 5 in square brackets, the determinant of A is just 5 also. Okay, so it's just 5. So basically, if you've seen one, you've seen them all on that. Okay, let's do something less trivial here. Let's go to 2 by 2 matrices. So this is where it starts to get interesting here. I've got a matrix I'm calling cap A here, and here you see I've designated the entries using the double subscript notation. Okay, so you remember here, small I, J, okay, in subscript. This is the element of cap A that's in what? The ith column, or the ith row and the jth column. Okay? Columns before rows. That's just how it goes here. That's been our convention. So I've got 1, 1, A11, A12, A21, A22 here. Okay, notice this is in square brackets here. Some people will use, I said, like parentheses. I like to use my square brackets here. Okay, what is the determinant of A? Notice, I forgot my parentheses here, but that's fine. The determinant of A is A subscript 1, 1, A sub 2, 2, minus A sub 1, 2, A times A sub 2, 1. In other words, this is, let me describe it this way. I've got the product of the main diagonal elements, okay, starting from the upper left down to the lower right. And from that, I'm subtracting off what? The product of the off-diagonal elements here in this 2 by 2 matrix, okay? All right? So you've got to get these in the right order because you do have a difference occurring here, right? Okay? So the product of the main diagonal elements minus the product of the off-diagonal elements. Okay, let me jump in here just real quickly. Another notation for the determinant, sometimes when you've got the actual entries of a matrix written out, such as I have up here, is the so-called bar notation, okay, where the determinant of A, like I've written here, can also be written this way. Do you see I've got 2 vertical bars? They look like absolute value symbols. Okay, 2 vertical bars, and then I've got the actual entries or elements of the matrix inside those vertical bars, okay? This indicates that you are taking the determinant, right, of this corresponding matrix up here. So this is a number. Notice I've written here, bars, not brackets. Brackets will have what? They'll have the little hooks on them. That is a bracket. This is just a bar, okay? But it means the same thing, A11, A12, or A22 minus A12, A21, okay? So it doesn't mean anything different. It's just a slightly different notation. Excuse me, this can be convenient sometimes. Let me show you a time where it's really not convenient here. If we had used that notation up here on 1 by 1 matrices, or 1 by 1 matrix, do you see I would have had what? The determinant of A looking like this, and if this was negative 5 instead of 5, do you see this would be what? This would look like absolute value signs, which would be what? 5. Okay? But if this was a minus 5 here, the determinant would be minus 5 also. Do you see what I mean? So this vertical bar notation is really lousy when you're dealing with 1 by 1 matrices, which we actually seldom do because they're essentially just real numbers. But just for the sake of completeness there, I'm showing you that that is definitely something we would not want to do with 1 by 1 matrices. But it is quite convenient when you're dealing with square matrices of higher dimensions here. Okay, let's be concrete now. Let's say the matrix B is the following matrix, 1, 4, 2, 6. You can see that's a square matrix, 2 by 2. You're asked to find the determinant of B. Okay, so I write it both ways here. The determinant of B, okay, and then I've used the vertical bracket notation. So I've got 1, 4, 2, 6 inside these vertical brackets. We know that means you're going to take the product of the main diagonal elements, 1 times 6, and subtract from that the product of the off diagonal elements, 2 times 4. And there we go when we get the final answer being negative 2. Okay, so pretty easy here. Okay, 1 by 1s are trivial, 2 by 2s are pretty easy. Now it's going to start getting a little hairier here when we get 3 by 3 matrices and higher. For the purposes of the exam, I'm not going to go any higher than a 3 by 3 matrix because it's just getting cruel. For higher order matrices, or even sometimes for 3 by 3 matrices, we would actually use a calculator or computer. Okay? All right, because it's just too much. It's too labor intensive. Before I actually start how we actually compute this, let's talk about the something I'm going to call the addition-subtraction pattern. Okay? For a 3 by 3. Okay, so I'm not literally, although I've got vertical bars here, I'm not literally taking a determinant right now. I just want you to see the following pattern. And this holds for all dimensions, actually. Okay? Of course, square matrices, though. Start in the upper left-hand corner, just for the pattern here. I want you to imagine that's plus, always. Okay? Plus, addition. Okay? Now, every time I move 1 unit down, any direction except for diagonally, to the left or right or up or down, I'm going to change my operation here. So this goes addition or plus, and then it's going to go what? Minus or subtraction, because I moved one place. Okay? I move another place and it's going to change again. It's going to go to what? Plus. Okay? Now when I come down here to this next entry, I would have what? A minus. And then what? Moving over, plus, minus, plus, minus, plus. Okay? All right, I'm not going to do anything with those right now, but in computing our determinants for 3 by 3 matrices, this becomes important here. Now, the same type of pattern holds for, like I said, higher dimensions. Okay? It actually holds for 2 by 2 matrices also, by the way. I'll show you that in a minute, though. Okay, anyway, same pattern, though. Same type of pattern. Start in the upper left-hand corner. That's plus. Move over, and it becomes what? Minus. Move over, plus, minus. Move down one place, plus, and then over, minus, plus, minus, plus, minus. Do you see the pattern there? Okay? Alrighty, so that's for 4 by 4s. And I'm not going to keep writing that, but we could, right? A 5 by 5, you would have what across the first row? Plus, minus, and then what? Plus. Okay? Now, when computing the determinant of a matrix, you can expand down or across any column or row, and you'll get exactly the same answer. If you have to follow this pattern above of additions and subtractions, though. Okay? Alrighty? Now I'm going to show you what I mean by expand here. What is he talking about? All right, I'll show you. Okay? First of all, I'm going to give the name D because it's a determinant. The determinant to this matrix, right? You see the vertical bars? So this is a number. It's not a matrix. It's a number. You can see the matrix I'm referring to, though, of course, sitting on the inside. You could write that in square brackets. 1, -1, 3, 7, 4, 2, 5, -2, 8, reading like a snake through here, snaking through. Okay, I'm going to talk about, just give you the example here. I'm going to quote unquote expand across the first row. Okay, now look at the first row. What is the first row? The elements are 1, -1, and 3, reading across left to right in the first row. Okay, now the first thing I'm going to do is the following. I'm going to see this 1 right here. Okay, that 1 right there. That is a multiplier. That is just a number, and I have it in parentheses here. Okay, now I've got what I'm calling a minor. Do you see that there? Minor, M-I-N-O-R. Okay, minor. Here's what I want to do. This is a determinant also. See those vertical bars? I've got 4, 7, -2, 8. Where did that come from? Okay, well, I'm going across the first row. I'm expanding across the first row. This 1 is in what? The first row and the first column, right? Now, I want you in your mind to imagine, I'm not going to draw on this because I'll really mess it up, but eliminate from what you see up here, this determinant. I want you to eliminate the first row and the first column where that 1 lies. What would you be left with if you just took an eraser and eliminated the entire first row and first column? You would have the determinant what? 4, 7, -2, -8. Or positive 8, sorry. -2 and then 8. Okay, do you see it? All right. Now, my next step in my expansion. Do you see this? This is vital. This is a minus. Okay, where does the minus come from? It comes from this pattern up here. See, there's no point in putting a plus sign in front of this thing. You're not really adding anything yet, but it's important to start out your pattern. My second step here is to do what? As I'm coming across, subtract. So that's where that comes from. Okay, the minus sign is coming from the pattern above. So while I'm here, I'm going to say in my next step, what do I have here? I have a plus sign. Okay, so it's really, all right, this is trivial, plus, blah, blah, minus, blah, blah, plus, blah, blah. Okay, and it's coming from this pattern right above using the first row. Okay, now I'm going to expand on the first column in a minute. Okay, but you could expand around any row or column and you'll get the same answer. Okay, all right, enough here. Okay, so I'm subtracting. And now what's my second element here in my first row? It's the -1. So I'm going subtract -1 times what? Get rid of it. That -1 is in the first row and second column. So get rid of the entire first row and second column. And what are you left with? 2, 7, 5, 8. Aha. Okay, use the vertical bars there because that is a determinant. Okay, next step we've already mentioned what? Is plus. Okay, from our addition subtraction pattern. What's the last element? 3. Okay, that's in the first row and third column. So get rid of those and you would have what? 2, 4, 5, -2. See how I have that? Again in vertical brackets. Now hold here. Now we're going to compute these and get a number because we know. Notice how I have 3 2x2 determinants to compute, but we already know how to compute 2x2 determinants, right? We did that above, okay? We did that previously. Now one thing I want to stop right here, I see students do all the time, and they will try to do this. For example, on this thing. Don't make this mistake. See the 3 here? I cannot take that 3 and multiply it on all of these elements inside and then take the determinant. Okay? You cannot do that. If you multiply that 3 on all the elements that's inside those vertical bars, you're going to be off by a factor of 3 to the first power in your answer. Okay? So do not try to bring that 3 on the inside. Got it? Do not try to bring that 3 on the inside. Same thing over here with this -1. Don't try to bring that -1 on the inside and multiply all these guys by -1. You're going to end up with the wrong sign. Okay? Just compute these determinants the way they are. Okay? So let's do it. I bring down the 1. It's 1 times. Now let's do this. Remember how to compute a 2 by 2. The product of the main diagonal elements, 4 times 8 is 32. Okay? And then we do what? We subtract the product of the off diagonal elements. So you can see that product is negative 14. Okay? Now the double negative here becomes positive, so I just wrote plus 1 times. Now let's compute this one. That would be what? 2 times 8 is 16 minus 5 times 7 is 35. Okay, try not to do too much at once. Okay, plus 3 times. Okay, 2 times negative 2 is negative 4. Subtract 4 times 5 is 20. So I've got negative 4 minus 20. Okay, now I work these out, and this is 46. Okay, this it turns out to be negative 19, so I'm adding negative 19. I just wrote minus 19. Okay, here I'm adding negative 72 as it turns out, so I just wrote that as subtracting 72. Put those all together, and I get negative 45. Okay, so that is the determinant of this matrix. Now I'm going to show you a shortcut for 3 by 3 determinants here in a minute. But before I do that, we're studying this pattern because this is the general pattern. This is the pattern that generalizes to, n by n determinants for any n. Okay? That's why this method is actually preferred to the shortcut. Okay? All right. Let's do this. Find D from the example above here. So I'm going to find the same determinant, but I'm going to expand down the first column. Okay? So I'm going to expand down the first column. I'm going to get negative 45 again, I claim. Okay? So now I'm coming down. Okay? Now the first part is exactly the same as this here. I'm starting with 1. Okay? Okay? And then I get what? 1 times the minor determinant, 4, 7, negative 2, 8, just like I have here. Okay? Now, always don't get this mixed up. These are vertical bars. I've seen people a lot of times, they'll start putting brackets on these like that. Don't do that. Then that would be a matrix. This is not a matrix. This is a number associated with a matrix. Okay? Got it? Okay? Now, what's the pattern here? I'm going down, right? Ooh, I've got to do what here? I got to subtract. Okay? So that's where this comes from. Okay? Okay? By the way, notice here in my calculation here, down here, I just grabbed our previous calculation. Anyway, so I'm subtracting. Okay? What is the value? 2. Okay? Now, find what the minor is. Get rid of the first column and the second row. We'd have negative 1, 3, negative 2, 8. Negative 1, 3, negative 2, 8. Okay, now the pattern on the pluses and minuses, we're going to plus. Okay, plus 5 times. Okay, because that's the last element here. I guess I should have rewrote this so I don't have to scroll back and forth. Sorry. Okay, but we're coming down here to 5. So you get rid of the first column and the third row, and we would get what? Negative 1, 3, 4, 7. Okay, all right. But we're taking the determinant of that. Again, my warning, do not multiply with the 5 through all the elements here, or with the 2 and all the elements here. Okay, don't make that error. Okay, we already computed this thing, so that was 46 from our previous calculation. Okay, and then I've got negative 2 times product here, negative 8 minus negative 6 is really negative 8 plus 6, okay? So I'm doing some signed arithmetic. Plus 5 times, here's negative 7 when I take the product here, minus 12. Negative 7 minus 12 is negative 19, so I've got that there. Okay, and now I did all the arithmetic here. What did I get? I got negative 45 again. Okay, alrighty, you might try this some other ways just for practice here. Try going down the middle column or something, or middle row, or third row if you want. If you do everything right, you should end up with what? Negative 45. It doesn't matter which row or column which you expand by, you're going to get the same answer, okay? Or you should. If you didn't, you did some arithmetic problem, okay? This is nice to know because, in some cases, you might have really convenient rows to expand it down. What if a row has a bunch of zeros, or a column has a bunch of zeros in it? That might be a good row or column to expand it down or across, right? Cuts down on your work. Because if you have zeros for these entries here, there's no real need to do any other calculation, right? We know 0 times any number is 0. So we wouldn't even have to compute the determinants of the minors associated with those elements. Okay? Now I was just to throw this in here, and one last example using the shortcut. For the 3 by 3 determinants, again, I'm taking the same determinant. So I've got 1, negative 1, 3, reading across, 2, 4, 7, 5, negative 2, 8. Now here's what you do. So you just write down the elements of the matrix that are inside the vertical bars. Okay, so you can see I've done that. I just wrote down that pattern. And now what you do is write down the first 2 columns in the correct order, like this. Okay, you could write the whole matrix again on the inside once again, but this last column is not going to do you any good. So just write the first 2 columns in the proper order that they came in. Okay, do you see the pattern? See how to create that? Okay. Now, here's what you do. To find the determinant of this the corresponding 3 by 3 matrix, to find D, in other words, here's what you do. What I did was circle these diagonals coming from the upper left to the lower right, and they consist of 3 numbers, okay? Do you see those? I've circled those in pencil. So I've got 1, 4, 8, negative 1, 7, 5, 3, 2, negative 2, okay? Okay, notice those appear down here. I'm going to take the products of those, and those are all going to be added together, okay? But there's going to be some subtractions too, probably no surprise in computing determinants. Do you see I've also created these other diagonals from the lower left to the upper right? Okay, so you can see here 5, 4, 3, negative 2, 7, 1, 8, 2, negative 1. These products are going to appear here, so I've got 5, 4, and 3, negative 2, 7, and 1, and 8, 2, and negative 1. But notice that what? These have a negative sign on the front. In other words, they're being subtracted, right? Okay? Or you could think about just the sign changing. But notice these are all what? Being subtracted here. Okay? We usually think of losing things as what? Going in the red. So I used red on this. Okay? I don't know if that's helpful. Okay, so you do the arithmetic here. It turns out to be 32 minus 35 minus 12 minus 60 plus 14 plus 16 because I've got negatives in here. We got some sign changes. So the double negative becomes positive. Anyways, you work it out. And I got negative 45 once again. Okay, so the determinant of that matrix, or should I say of the corresponding matrix, I guess I wrote it originally as a determinant, but that determinant is negative 45. I think we've beaten it to death, didn't we? Okay. Okay, now this shortcut does not generalize, okay? It does not generalize. It's only going to work for, 3 by 3 matrices. Okay, it doesn't generalize. That's why people don't like to use it quite so much. But this thing I did here with the patterns of pluses and minuses, this is completely general, okay? It always works, okay? So the more powerful notion is the addition-subtraction power method there. Okay? All right, let's talk about some properties of determinants. I'm actually going to mention this when we deal with Cramer's rule, which is going to be an application of determinants coming up next. I didn't actually do an example here, but I probably will in the next video. Adding a multiple of one row or column to another row or column, respectively, leaves the determinant unchanged. Okay? So you might do that. You might come up here, maybe take an easy one. Maybe this one. Add a multiple of the first row to the second row, like 10 times the first row added to the second row, but leave the first row unchanged, and you'll get a new matrix. Take its determinant, and it'll still be -2. Okay? Or whatever the determinant happens to be. Okay? Interesting. This is a fact. None of this is obvious. Okay? Remember, these are what? Determinants are only defined for square matrices here. Okay? But the determinant of the transpose of a square matrix is going to be the same as the determinant of that matrix. Okay? The determinant of the transpose and the determinant of the original matrix are equal. Interesting. Okay? If A and B are square matrices of the same dimensions, so I can multiply them. Okay? The determinant of the product is, believe it or not, the product of the determinants. Not obvious in the least. Okay? Notice that since these would be what? Square matrices of the same dimensions, both BA and AB would be defined, right? And they notice that the determinant of BA, because the determinant is multiplicative, would be the determinant of B times the determinant of A, but because those are just numbers, and numbers in multiplication are commutative, that this has to be the same as the determinant of BA. So the determinant of AB is the same as the determinant of BA for square matrices of the same dimensions A and B, even though AB and BA themselves, as we've already stated, will probably be completely different matrices, right? Well, not completely different. They'll have the same dimensions, but their entries might be quite different, right? We've seen that before. But they'll have the same determinant, okay? So the determinant is actually multiplicative. It is not additive, however. I just want to throw this in here. If I take the determinant of two square matrices, okay, and I go the determinant of the sum, it is not generally equal to the sum of the determinants. It's not additive, okay? This generally does not work, okay? Generally, these two are different, is what I'm saying, okay? You could try any concrete example that you want, and the chances are quite good that you're going to get the two sides being different, okay? So generally, there are some instances where they could be equal again, but generally they're going to be quite different. Just a quick little fact here. I'm not going too far into this. The area of a triangle in the Cartesian plane. Suppose I have 2 points with coordinates A, B, and C, D in the Cartesian plane. The area of the triangle formed by those 2 points in the origin is half the absolute value of this determinant. A, B, C, D. Okay? All right. I could have taken the transpose of that matrix that's on the inside of the vertical brackets or the vertical bars, and that would work too, right? Because of that number 2 property. Okay? All right. Now I'm taking absolute value because you usually want area to be positive, because some of the determinants we've seen are actually end up with negative values, but it's half the absolute value of the determinant. Okay? This thing's actually the area of a parallelogram formed by these points and the sum of the 2 points, but I'm not going to go into that. Let's, for example, find the area of the triangle formed by the origin, so 0, 0, and these 2 points, 1, 2, and 7, 3. We'll go ahead and just write them down, 1, 2, 7, 3. Take that determinant, okay, so that'll be 1 times 3 minus 2 times 7, so that's 3 minus 14, that's negative 11. Take half the absolute value of that thing, so half the absolute value of negative 11. Notice that dangerous notation, right? Okay, you get 5.5 units. So the area of that triangle, if you were to draw that out, would be 5.5 units. Okay, this whole notion can be generalized. For example, if I have the origin and 3 points in 3 space, Cartesian 3 space, then 1/6 the absolute value of the determinant formed by those 3 points that have what, x, y, z coordinates, is going, so there'll be a 1/6 of a 3 by 3 determinant. That ends up being a volume of a tetrahedron, actually. Okay, so believe it or not, these determinants are telling you something geometrically, actually. But that's not really how we're going to be using them much. Okay, next up we'll do something with something called Cramer's rule, solving systems of linear equations using determinants. Okay, well, I hope you understood this, and look at those problems quickly.